This is Unit 4, Lesson 6, Part 1, L'Hopital's rule. Now, L'Hopital's rule is great when you're doing limits because it handles some of our indeterminate forms. Now, when we were doing those in Unit 1, we had to kind of like look a little less than the point we were looking for and a little more and try to figure out what was going on. So this gives us a direct way to handle some of those indeterminate forms. You want to remember that there are 7 indeterminate forms, but the only 2 that L'Hopital handle is the first 2. If you have a situation where you have 0 over 0 or infinity over infinity. Other than that, the other 5, you're going to have to find a different way to evaluate the limit. So the actual rule of L'Hopital states that when f of x over g of x has an indeterminate form of the type 0 over 0 or infinity over infinity, and of course that can be negative infinity over negative infinity at a particular value, then we can replace f of x over g of x by the quotient of the derivatives, and we'll take that limit. Okay, so here it is formally. So we're going to assume f and g are differentiable on an open interval containing c, and of course g prime of x cannot equal 0, because if it does, then the derivative will be undefined as well, because it will be in the denominator. And so what we know is that then if the limit as x approaches c of f of x is 0 and the limit of f approaches x approaches c of g of x is 0, then this is what I'm saying, we can replace the f of x over g of x with f prime over g prime. And the same is true if you have the indeterminate form of infinity over infinity or infinity over negative infinity. And of course it can be near but not equal to c, and of course this works for one-sided limits as well. Okay, a couple of cautions. In order to use L'Hopital's rule, you have to make sure these conditions are met. So this is one of those things for the test, and I'll get to that in more detail in a second here. You have to, it has conditions, so on the test you have to make sure that you state that the conditions have been met. So if g prime of c is not equal to 0, then the limit is undefined, okay? You can't use oscillating functions. That has to approach a single y value. And also that the limit is going to be undefined if the ratio is not equal to infinity. So we'll get into that as we go through some of the problems here. Now, this is the update for the new exam. So you have to show the proper steps and notation. Okay, so you want to have to explicitly show that you've got 0 or infinity for both the numerator and denominator, so you have that indeterminate form. You have to state that it's the indeterminate form and then say you're using L'Hopital's rule. And you want to make sure that you show that equality as well. And of course, use proper limit notation as well. So I'm going to, for the first couple examples, I'm going to use a lot of detail. And then when we get to example 4, I'm going to show you how you can just flow through a problem, have everything in there, and not be obsessed with how detail-oriented you are for the test, for using the right notation. Okay, so this section is divided up into the different types of indeterminate forms as well as the different types of functions. So polynomials and powers. The first one, the limit as x approaches 5. So what we want to do is take the limit of the numerator and the limit of the denominator. So we want to do that first. This is why we're specifically showing that we know that it's going to equal 0. So we can say that this is 0, and then we'll do the same for the denominator. I mean, if you want to show all the intermediate steps here, like if you want to show that's supposed to be an arrow, if you want to show 2 times 5 squared minus 9 times 5 minus 5. So you get 50 minus 45 minus 5, that equals 0. Go right ahead. But this is enough information right there if you can do that. Then what we're going to say is we have to state that we have an indeterminate form. Sorry, I keep hitting my watch when I do this. So you have to state that we have an indeterminate form. So you're going to say that the limit as x approaches 5 of 2x squared minus 9x minus 5 over x minus 5 is equal to 0 over 0. It's indeterminate. And then you're going to say by L'Hopital's rule or applying L'Hopital's rule. So we're going to say the limit as x approaches 5 of 2x squared minus 9x minus 5 over x minus 5 is going to equal to the limit as x approaches 5. And then we just take the derivative of the numerator and denominator. So we get 4x minus 9 over 1, and then we can do our direct substitution. So this is going to be 4 times 5 minus 9, which equals 11. Okay, so that's how we're going to do it. Let me just go through and flow through how one of these work. So you can just go ahead and you can show that you're taking the limit as x approaches negative 5 in this problem of the square root of 4 minus a negative 5 minus 3 over negative 5 plus 5. So you're going to get the square root of 9 minus 3 over 0, which is 0 over 0. So you can say indeterminate form. And then say applying L'Hopital's rule. We're going to have this then. The limit as x approaches negative 5 of our original function, our original rational function, is going to equal the limit of the derivatives. The bottom's easy, that's 1. The top, we're going to bring the power down, which is 1/2, lower the power by 1, which will be x minus 4 to the negative 1/2, and then, whoops, it's 4 minus x, sorry. And then the derivative of the inside, which is negative 1, and then the derivative of 3 is 0. So this is going to equal the limit as x approaches negative 5 of 1/2 4 minus x to the negative 1/2. You can just make that negative. So then substituting, we get negative 1/2 times 4 plus 5 to the negative 1/2. So this is going to equal, oh, I forgot the square. No, I'm good. I have the power, not the square root anymore. So this is going to equal negative 1 over 6. That's a little box. See, this is what I need. I need a big box. Okay, what if we have a function like e to the x, or we have a power function or a polynomial function that is still going to be indeterminate form, 0 or infinity, after one use of L'Hopital's rule? The nice thing is, if the function is nth degree differentiable, you can keep taking the derivative of it till you get to a form that you can take the limit of. So in this case, we're going to have to use L'Hopital's rule twice. So we'll start by substituting in, and what we're going to get when we do this is we're going to get infinity over e to infinity, which is really infinity over infinity. Because remember, e is an exponential growth function, so it's just going to grow. So this is an indeterminate form. So applying L'Hopital's rule. The nice thing is at least we don't have to say that the functions are differentiable and all that stuff. So our limit is now going to become the derivative of our numerator and denominator. So we're going to have 2x over negative e to the negative x. And so when we go to evaluate this, we're going to get negative infinity over negative infinity. It's still indeterminate. So we can do L'Hopital's rule again because both the functions are differentiable. So applying L'Hopital's rule again. So we're going to get the limit as x approaches negative infinity of 2 to the x over negative e to the negative x is going to equal the limit as x approaches negative infinity of 2 over e to the negative x. So now the numerator is no longer indeterminate. So what we have here is we're going to have, and you don't have to show the work for this, this is going to be a very large number. So 1 over a very large number is pretty much 0. So if you think about it, if you have a fraction like 1 over 1 million or 2 over 1 million, this is very, very close to 0. So that's how you look at that. So you can just put that it equals 0. You don't even have to state that. You can just put that for it. Okay? Let's assume that you understand that. All right. So now let's look at number 4, where we have a third-degree polynomial. So we're going to have to use L'Hopital's rule twice. So good times, good times. So let's go ahead and let me move this back. Let's go ahead and substitute in our negative 2. So we're going to have negative 2 to the third plus negative 2 squared minus 8 times negative 2 minus 12 over negative 2 cubed plus 8 times negative 2 squared plus 20 times negative 2 plus 16. So the top becomes negative 8 plus 4, so that's negative 4, plus 16, which is 12. 12 minus 12 is 0. I don't know why I have that delay. So we get a 0 here. And then same thing in the bottom, we have negative 8 plus 32. So that's 24 minus 40 is negative 16 plus 16, so this is 0. So this is the indeterminate form. So this is indeterminate. Okay, so applying or using L'Hopital's rule. We get that the limit as x approaches negative 2 of x cubed plus x squared minus 8x minus 12 over x to the third plus 8x squared plus 20x plus 16. And let me clean this up because this is not looking good here. Much better. This is going to equal the limit as x approaches negative 2 of the derivative. So let's take the derivative. So we get 3x squared plus 2x minus 8. And in the denominator, we get 3x squared plus 16x plus 20. And now when we substitute again, we're going to get 0 over 0, which is indeterminate. And applying L'Hopital's rule again. And like I said, you can just keep going with this. Or you can reason your way through this, and we're going to do that later. So our limit as x approaches -2 of 3, x squared plus 2, x minus 8 over 3x squared plus 16x plus 20 is now going to equal, let me just change colors, keep this kind of easier to read, is now going to equal the derivative of these two functions. So we get 6x plus 2 over 6x plus 16. So now when we substitute, we get 6 times -2 plus 2 over 6 times -2 plus 16. So we get -12 plus 2, that's -10. -12 plus 16 is 4. So you can leave your answer that way, or if you want to reduce it, you can reduce this to -5 over 2. Okay, so you can keep going with L'Hopital's rule, that's the thing. Okay, so I'm going to stop here and then continue with our trig transcendental functions in the next video. And then I'm going to finish up in the third part of the video with some AP style questions.